Можете сейчас через секунду проверить, что yeah, so it is integral both its fraction field and so dimension, proof dimension of A is equal to 1, meaning that every non-zero prime ideal is maximum. So then we have proved that any ideal can be decomposed into the product of prime ideals in some powers. So there exists decomposition. And notice that, yes, so actually what we're proving, yes, so that we have assumed that, so here we use Noetherian property, so that we have assumed that I is maximal without this property, then we have supposed that it is not prime, then we found two elements that those product inside I and there, but they are so, but they are not inside the I, and we took the product, and we have first of all we have enlarged the ideal, and then we have obtained the I as a product of such ideals. So this. Yeah, actually, not exactly. Yeah, so, я maybe. Я что-то забыл, я это же успел доказать или нет в прошлый раз, извините. Или мы только про обратное поговорили?
Мне кажется, мы только на обратное.
Да, мы только про обратное поговорили. Да, давайте вот,
да, вот насчет этой теоремы, мы как бы начали доказывать лемму, cancellation лемму.
Да, давайте, да, я еще да, мы тут не договорили, да. Yeah, so, sorry, this is, so we haven't proved this theorem so far. But what we have proved, yeah, so what we proved, so what we proved is the following. So first of all, we have, so if pi is prime, so prime ideal, then it is invertible, so there exists pi inverse, so that is not equal to O, so it is strictly larger, and pi times pi inverse was equal to O. And what we also have proved so far is that we proved that any ideal is invertible. So this means, notice that we have introduced fractional ideals, and P inverse was fractional ideal. So we proved that pi I is invertible in the group of fractional ideals. And also we have taken I, so arbitrary ideal, and we have proved that I inverse is not, so is not equal to O, and there exists I inverse, and I inverse times I is equal to O. Yeah? And also we have proved the uniqueness of ideal, so of such ideal that if you have just if I is inside O and there exists J such that I times j is equal to O. Yeah, so this implies that j is inverse. Yeah, so j is inverse in the sense that we have introduced. Yeah, so j is inverse to I. Yeah? J is inverse to I. Yeah, so where I inverse, yes, so let me recall that I inverse is simply the characterizing condition. So x belong in the fraction field of A, so such that x times I lives inside of. So then we have also proved the cancellation lemma. So let me recall it. So so if I divides j, if and only if, so meaning that there exists k such that. So here I mean that k so divides in the not in the sense of fractional ideals, where all ideals are invertible, but there exists k inside O such that j is equal to I times k. So this happens if and only if we have I. So I is the just I contains j. So one can speak about this kind of the property of divisibility, which is actually stronger than just the container. So also, yeah. So also there is a. So let me recall that there is a principal theorem on arithmetics. Principle. Of arithmetics. For ideals, yeah? For ideals, and actually, so this is of course a generalization of the property that just if P divides AB, then P divides A, or P divides B, and that was the just well, of course, this is for integer numbers, and the principal theorems of arithmetics generalize this observation. So, meaning that if you have, so it is in the sense that P so divides ij, then P divides I, or P divides j. Yeah? And here, of course, we reduce, since we have this kind of cancellation lemma, yes, so that we simply can reformulate that P divides this just in the property that P contains ij, yes, so that means that we can, so by reverse lemma, we can say that pi contains ij, and actually, well, we will be interested. So this is evident actually part of that lemma, but we shall use in the converse of the statement. So then this implies that phi contains I or phi contains J. And this is just due to the fact, so the note that we have even more general statement. So we call more general, even more general statement that can be actually derived out of this. Yeah? So, and to prove this, you just take A, which is inside I but not in P, and B, which is inside J but not in P. So the product AB is inside IJ, but AB is not in P. Yeah? So also recall more general statement, which also can be proved explicitly by this kind of argument or iteration, that if P contains the product of ideals, so we have used this part, then P contains some. So P contains contains I for some I. Yeah, so
What is the previous lemma that we...
yeah. So previous lemma says that, so notice that here I'm writing down the word divides, but formally, yeah, so if you want to speak about division, it is equality like this, yeah? But we have used inclusion 2 instead of this. So that's why, yeah, so this means that, so here in this lemma we should write divide, but we have proved inclusion. And this implies, of course, so that, so this, by previous lemma, this implies divisibility. Yeah, so actually, yeah, so we have formally just obtained the, so formally used the Wicca property, and we obtained Wicca property, but then we have derived a stronger one out of this lemma. And so morally, yes, so that the crucial thing is this kind of statement, but we have, yeah, so we need more precise result. And so let me speak about uniqueness of the composition. Of the composition. Yeah, so this is of course also, so this should be proved as in arithmetics, but with some small modifications. So of course it uses two things. Yes, so the first it uses principal theorem on arithmetics. And also it uses existence of so that any ideal is invertible. So existence of inverse of ideal yeah, so mainly existence of prime inverse of prime ideal. And of course this should be like this. So assume that you have two decompositions. Yeah, and of course, so clearly, P1 contains this side. Yeah, and so this implies that one of the ideals should be for the right hand side that P1 should contain Qj for some J. Yeah? And this means yes, this is principal theorem on arithmetics, and yes, so this lemma. And then this implies, so from maximality, so Q J is maximal ideal. Yeah, so any prime is maximal. So this implies that actually P1 is equal to Qj. And then we can just cancel this decomposition. So just multiply by P inverse. Yeah, so of course assume. Yeah, so assume that J is equal to 1 for notational purpose. Yeah, so you are writing down by P1 inverse the product P1 Pn and P1 Q2 QR, and we multiply it by P inverse, so you get P2 etc. Pn and Q2 etc. QR, and then just argue by induction on the number of ideals. So argue. And then the proof itself, yeah, so is very easy. So the theorem, so the last statement about the existence of decomposition. So existence.
Кажется, existence мы как раз доказали.
Да, ну давайте я напомню, как именно. So existence of decomposition was like this, yes, so that we just take maximal I without decomposition. P is not prime, so I is not prime. But we have assumed that I contains just the product of primes, and we have just taken one of them and multiplied by P. So we take P inverse, so pi is equal to pi 1, and we have taken P inverse of I, and we have noticed that it is larger than I, so it has decomposition. However, we have to derive that if you take so pi inverse times I is not equal to I. Yeah. So notice that pi inverse I. Yeah. So it yeah. So that was the point. Yeah. So. Yeah, maybe that was um, yeah, sorry, here not like this, so I was contained in pi. Yeah, so we have to, yeah, so I forgot to say that for I, so how pi was taken not in this decomposition, yeah, so pi was taken, I was not prime, yeah. So it, I was contained in some maximal ideal pi, so in some maximal ideal pi. I have forgotten if I have stated this. Yeah. So so any ideal is contained in some maximal ideal. So I is contained inside in pi. So this implies that, yeah, so notice that we have two things. Yeah, so first of all, if you multiply this multiply by pi inverse, then you have I times pi inverse is a subset of pi times pi inverse, and this is a subset of O. So this is still ideal. So ideal in O. In O. So notice that multiplying by pi, so can make so it definitely makes the ideal larger. Yeah, but you have to control that still you, in order to use the induction, yeah, so you have to control that still your ideal is inside. So it is still the ideal after this multiplication. And this is larger than I, since otherwise, so if you just take that, so there is inclusion, so since unit belongs to P inverse, so this of course, so here of course you have inclusion of, so this is larger ideal, and P inverse of I is not equal to I, so here we use integral being integer closure. So since A is integrally closed, so otherwise you have inclusion. So actually you have equality, but it is sufficient to use the inclusion. And this implies that any x of NP inverse is integer over A. And this implies that yeah, so this is contradiction. So so contradiction. Yeah, so this implies that x is integer over A. So that means that x belongs to A, yeah, because any integer elements over A in the fraction field belongs to A. So this contradiction with the property that pi inverse is not equal to A. Sorry, O is A. Maybe that. Yeah, so just. So yeah, so this proves the existence. Yeah, so we have recalled the existence of the decomposition. I think I have stated it, but I don't know precisely recall if I said everything here. So also, yeah, so also there is a corollary of what we have said, which is important. So corollary. Yeah, so that if you have I that contains J, Yeah, so inclusion of fractional ideals. Yeah, so similarly, you can prove that any fractional ideal is can be decomposed into the product of prime for very simple reason. Yeah, yeah. So let me just put the remark. So since we haven't discussed it, yeah. So suppose I is fractional. So that means that there exists C that is in. So you can assume that C is inside O, yeah. So that is inside A. So such that C times I is inside A. Yeah. So this is ideal. Yeah. And then you can decompose I in the product and C in the product. Yeah. So sorry, C you can you can decompose C in the product of because it is element of A. Yeah. So this let me write it down like Q1 L1 QR LR. And we can decompose, So, and we decompose CI, C times I as the product, so P1 and 1, etc., P, K and K. Yeah. So then the ideal I itself can be obtained as E1 and 1, E and Pk and K divided by, yeah, so meaning that you are writing down inverse, yeah, so you, meaning that you are writing down Q1 inverse in L1, etc., QR inverse in LR, and this is just the required decomposition. Yes, so we can, since we have proved the some uniqueness property, so that for inverse, yes, so that it is just, I mean, sum of P can cancel, but this with Q's, but you can write down Q in minus L1, etc., minus the degree minus LRR. Yeah? So at least any fractional ideal can be decomposed into the product of prime ideals. And if you have inclusion of ideals, yeah, so that so corollary is more or less now evident that for decompositions, so then there exists decomposition P1 and 1, P, K, and K, and decomposition of J, P1, M1, etc., P, K, MK, yeah? And what you have to assume that simply that you see I is larger, yes, so then N1 is smaller than, so this implies that N1 is smaller or equal than M1, etc. MK is smaller or equal than MK. This is just, I mean, direct proof by divisibility lemma. I mean, you can reduce this to non-fractional ideals and use divisibility lemma. And divisibility lemma implies, of course, that yeah, so divisibility lemma can be formulated for fractional ideals as well. Yeah?
Mhm.
So also a cancellation lemma is valid. Cancellation lemma holds for fractional ideals.
And then in cancellation lemma we mean that this, so I divides j, that means that exists k
K in O, yeah?
in O.
Still
For
in O.
fractional ideal.
Yeah, because for fractional ideal, it is, divisibility, it is now a group, yeah? So for fractional ideals from the group are under multiplication. So in this sense, they are all divisible by each other, yeah?
Mhm.
But if you formulate this lemma for inclusion in A, yeah, so that means inclusion implies that there is k such that,
Mhm.
yeah, so I just want for the audience to emphasize your question, yes, so notice that, yeah, besides, yeah, so that is, yeah, so,
Isn't
So-
here if I and j fractional ideals, k should be also fractional ideal?
there's no reason because, if your ideal is fractional and is an A, it is ideal.
Yeah, that's true,
So-
but
There is, if you think about this divisibility without this condition, yeah, so then this doesn't make sense because, you can also always write down for k, yeah, so you can also write down j I inverse, but you should have some properties, yeah.
uh-huh.
And so in order to have this kind of inclusion, you have to impose some property of k, and this property is inclusion in k.
Окей. Нет, ну я просто не понимаю, вот смотри, мы возьмем I, там, pi n в степени I, и k еще каких-то pi добавим, да?
Да.
Вот. Разве у нас же не станет как бы, содержать и наоборот? Тут ты утверждаешь, что и содержится,
Тут,
что же содержится в и.
Ну, тут может опечатка сейчас. И делит жизнь, да? Ну, вот это правильно написано. А теперь и побольше, да, идеал, потому что вы взяли и умножили еще на что-то, идеал уменьшается. Ну, при умножении на другие идеалы, идеал уменьшается. Да, более делимые числа, они же, ну, как бы...
Ну да.
естественно.
Ага, да, точно.
Поэтому, ну, как бы вот тут, это вот условие очевидно, а как бы не очевидно вот, наоборот. То есть, ну, как бы вот, то есть там неправильно написано. Вот, соответственно, ну вот, как бы вот с этим мы разобрались. Yeah, so then I want to discuss the following proposition. So it says that the proposition. It says that that Dedekind ring with finite number of prime ideals or maximal ideals has a very special nature. So that suppose A is Dedekind ring. With a finite number of prime ideals, this implies that A is principal ideal domain. So all ideals are principal. Yeah? So how we should prove this? Yeah. So yeah. So now we have. Yeah. So notice that. Yeah. So now we have the following. So let me prove. So the proof is based on the following observation that if you have P1 etc. Pk, so this is a full set of prime ideals. Yes, so just full collection, not exceptional of prime ideals. Yeah, so this, yeah, notice that they are pairwise coprime because they are maximal. Yeah? So they are pairwise.
So it's without zero.
Yeah, without zero. Yeah? So pairwise coprime, since. Yeah, so just they are maximal. And coprimeness means that pi plus pi g is equal to the whole ring. And of course, yeah, so if pi doesn't contain pg, yeah, then notice that they are all maximal. Yeah, so this means that pi cannot contain J, otherwise they are equal. Yeah. So for I is not equal to J, and moreover, so you have obtained pi I. You added some element, but pi I was maximal, so you obtained the whole ring. And by observation that we made in principal ideal in Chinese remainder theorem, so observation from Chinese remainder theorem. Then you have pi I and 1, etc. pi k and k are pairwise coprime. So this means that yeah. So notice also. Yeah. So now how obtain principal ideals? Yeah. So that suppose yes, you have start with so start with I equal to the product P1 K1 etc. PS KS. And you want to understand which element should be principal here in order to prove that any ideal is principal. Yeah? So which is generating element. And notice that there exists, now this I will explain later, but so there exists pi I tilde that belongs to pi I ki without pi I ki plus 1. Yeah, so this of course, notice that yeah, so in that they can drink we have cancellation property. Yeah, so that means that already we know that equality. So pi I ki is not equal to pi ki plus 1 I from existence of from uniqueness of decomposition in primes. Но это лемма Накаяма, вообще говоря, ну, как бы ее интерпретация, но у нас... Да.
Ki plus 1 это просто следующий.
О, да, неправильно.
Плюс 1 должен быть.
Да, наверху. Ну, он у меня здесь правильно написан.
Да.
Спасибо. Вот, ты тут покрупнее, да. Yeah, so this follows from uniqueness of decomposition of decomposition. То есть, ну, это вообще говоря, so for those who know, this is just Nakayama lemma, but some part of it, yes, so because in order to use Nakayama lemma, you have to use that your ring is local, yeah, but in order to have it local, you have to localize, yeah. Mm-hmm. But notice that also this equality can be stupid, yes, so since stupidly. So this implies that this equality is not possible only after localization. Yeah? Mm-hmm. But so of course this will be sufficient for existence of pi, mm-hmm. Yeah? Because this equality is not possible. This is so. If this equality holds in our ring, then this equality, of course, holds after localization. But this doesn't. That uniqueness of decomposition is a little bit stronger because we know that this equality is not possible, but it can happen that this equality doesn't hold in the local ring, mm-hmm. when you localize. But the ideals could be not equal, but after localization they become equal in the local ring. Yeah, so that is possible. So, for example, you can multiply so maybe later I shall be talking about this. So. So we start with the choice of such elements, and then you just notice the following, that you can form. By chain, notice that we have done it for all possible S. So we find by Chinese remainder theorem. So by Chinese remainder theorem, we find alpha. so such that equal to pi tilde modular, so precisely this k plus 1 ideals, yeah, so p I k I plus 1. So, yeah, so since they are coprime, we can do it. Yeah? So this now we have to compare alpha and I. Yeah, so that we can write alpha, and this is now. So this is precisely the place where you use finiteness of prime ideal. This is most important step here. Yeah, so because the alpha, so again we can apply by principal theorem on arithmetics, so the existence of decomposition of arithmetic. Yeah, so we can write down this as P1, etc., S, LS. Notice that these primes are precisely the primes of the decomposition of I.
So there's always, when we write S, we should write K. That's since we have only K ideals.
Да, тут я чего-то. Я понял, я тут. Давайте я, вместо К S поставлю, потому что уже поздно. То есть как бы P, S, NS. И вот тут тоже PS поставлю. Ну, да. То есть, so the most important thing that this set of primes is the same. So what you know that note that yeah, so this of course yeah, so clearly this is a subset of P I L I. So I mean any so for any I, and you can look at so notice that if Li is bigger than K I, so this implies that alpha is equal to 0 modular Pi Ki plus 1. Сейчас. Ну, то есть, как бы, если вот эти вот штуки больше, чем вот эти степени, да, а альфа, оно, да, но, but notice, note that alpha is equal to Pi tilde modular Pi Ki plus 1. So which is which is not 0 modular, so which is not 0, but alpha is 0 modular Pi. Yeah. So, but alpha is equal to 0, so modular Pi Ki. Yes, so since so Pi's were taken from Pi Ki, yeah? So from the beginning. And this implies that so this check, yes, so tells us, yes, so this is check modular any prime component, and notice that alpha, this implies that alpha belongs to the intersection of Pi Ki. So on one hand, we know that so this implies that Li's are smaller. Yes, So if Li's are bigger than alpha is 0 modulo Ki plus 1, which is not true, so this implies that Li's are smaller or equal than Ki. We have found this bound, yes, so from this condition. But also alpha is 0 modulo Ki, so this implies that alpha is in the intersection of prime ideals, so then we use that it is in the product. Yes, so the intersection is equal in the product for coprime ideals. So for pairwise coprime ideals. And the last one is already I. Yes, so that yeah, so what we have obtained that alpha is inside I, and we have decomposed this as the product of P1, L1, etc. P SLS, and this we have decomposed as P1, K1, etc. P S KS, and we have noticed that LIs are less or equal than KIs, but this LIs, yes. So, but this inclusion is opposite for this condition. So the inclusion implies so the inclusion implies that they are equal. Yeah. Actually, already inclusion implies opposite condition. So this. But again, I mean, we do not use it in full generality. I mean, already you have. I mean, we do not use cancellation lemma here as it is, but we can recall it in our mind. Yeah, because simply you are using that you have Li's are smaller or equal than Ki's, and since you have this kind of inclusion, it should be equal. Yeah, so otherwise, just I mean. Because inclusion Li is less or equal than Ki implies the converse inclusion. Yeah, so this implies that alpha is again contains I. So the main point, of course, it occurred here because checking of course we have to understand here what happens if there is infinite number of prime ideals. So precisely it happens here, so that we have taken alpha, have used conditions only on the finite number of PIs, yeah? But then we have taken alpha and decomposed it in the product of primes. If we had infinite number of prime ideals, there would be ideals that we didn't use to write down the previous conditions. So finding alpha can with this kind of condition it can happen that precisely in this decomposition there will be new ideals that do not occur. So we cannot write this bound. Yeah? So we can bound them only for indices that are for our finite set of ideals, but we cannot control other components with other prime ideals, so we cannot speak about this kind of inclusion. Yeah, so corollary of this so is that so corollary. Suppose you have one prime ideal. Yes, so suppose E is local ring, local Dedekind ring. So local that I can drink. Yeah, so the ring was only one non-trivial prime ideal, so M is only non-trivial prime ideal. So you see that this is principal ideal domain. Yeah, so meaning that any I can be written as the power. First, so we use the composition that any I can be written as the power, and previous statement allows us to find actually. So actually, after writing down I as this product, you need only to generate M by one element. Yes, so and M can be generated by X that belongs to M without M squared. So again, M is not equal to M squared due to existence of decomposition. But but this is even due to Nakayama lemma. So let me recall it. Due to Nakayama lemma. Yeah. So this. Yeah. So M can be generated by X because we can take such element. Take this element and actually we can repeat the previous argument, which is a little bit easier here. So you take this element that belongs to M square, and so this means that X can be written as the power of maximal ideal for some K. But since X so since X is not inside M square, yeah, so that means that K is equal to 1. Yeah, otherwise we can have this kind of conclusion. So this means that X is, so X generates M, and then you take any ideal and you write down the decomposition. Also, well, in Land book, for example, you, I mean, so, or somewhere, I do not remember, either it is written in the Land book or somewhere in the exercises. I mean, as an exercise and solution to the exercise or comment to solution, I do not know. Yeah, so that was the point of choice PI. It was less clever because I mean it is actual auxiliary step which is not needed. Yeah, so you can search for pi tilde to be generators of pi. Yeah, so that means that I mean potentially generators. Yeah, so you can take pi inside pi without pi square. And then you can find, instead of these PIs, you can take the powers of PI, but it is not needed for this formulation because I mean better to use more general theorems, which are just always true. I mean, like coprimeness of powers, etc. I mean, because there's some kind of checks that have to be done. That I mean, if you have PIs which is in PI but not in PI squared, then the powers should be precisely here. So we have to speak about it. But I mean, the main point not in this part, but main point is that you in order to, so this two moments, yeah, so just that you can check this decomposition component-wise, yeah, because you have this kind of product, and so the possibility of finding such for this division properties. So actually here we also proved that in a theorem, yeah, so that so here we proved the important thing, so which is quite non-trivial theorem to prove it directly. So this one is not so easy, I mean, and if one thinks how it should be proved, it is more or less minimal way to prove it. And so, I mean, of course, you can, I mean, in the course of proof, you can prove explicitly the existence of such decomposition for Dedekind ring, and then you, I mean, for local Dedekind ring, and then you can derive it. And moreover, you can, if you can think of localization, you can prove the property of the composing ideals. Yeah, so by thinking that you can check the power, just yeah, so yeah, so you can do that. You can take I and take this decomposition. So and one. So k. And so yes, maybe let me write down this remark. Yeah. So yeah. So suppose you have this kind of decomposition. So then how to obtain the multiplicities? So how to make control on the multiplicities? And so how to check what are they? So I mean, Dedekind ring could be quite complicated, but you can reduce the situation to the local ring. In order to do it, we have let us recall construction of localization. So construction of localization. Yeah, so I mean, I won't go in much of the details. So given A and S is multiplicative set, meaning that S and T belongs to S. This implies that the product belongs to S, and the unit should also belong to S. So this allows us to form, so here you won't have zero divisors, so we can write down the localization is the set of pairs. So with so these are so with equivalence relation. That so AS is equal to B here. So let me formulate it in general setting. If there exists U, so such that U times AT minus BS is equal to 0. Yeah, so U. But if you do not have zero divisors, of course, so only it is enough to write down that AT is equal to BS. And if you have this kind of equivalence relation, then you can ask yourself what happens with, I mean, yeah, and also you have natural inclusion. Natural map of A into AS, meaning that you map A into the pair A1, and so usually people write down this as a fractions, and well, of course, the property, so this AS is the ring, and you just, yes, you add like the fractions, so passing to the common denominator, and you multiply as you multiply the fractions. So also you can ask yourself how spectrum is changed, so the set of prime ideals. So you have the set spectrum of A, and you have spectrum of AS. So given ideals so what I say that the spectrum of AS, there is a natural inclusion in the spectrum of A. So this is done as follows. So you can take a prime. So I mean, if this is just I, yes, so given a prime ideal pi here, yes, so then you can map it to I inverse of pi, and this will give the ideal with the property. So this is a prime ideal such that S, intersection of S and this ideal is empty. So spectrum of AS can be identified with the set of prime ideals in spectrum of A, and so such that so you can think of I of spectrum. So maybe so I has maybe I, but to write down this as I inverse, yes, so that I inverse of spectrum of AS is the set of prime ideals in the spectrum of A, so such that pi intersection of S is empty. Yeah, and so this geometrically, this can be viewed as follows. If set S is finitely, so geometric interpretation. That so S can be thought of finite. I mean, S can be infinitely generated or finitely generated, but if S is a finitely generated subset, so you have the elements and you consider all powers of elements. Yeah, so then this set can be, so the spectrum of A is just the full set written here. So you can think of this as algebraic variety, and you cut out, so Si can be thought of equations, yes, so it's polynomials. So you cut out the sets, yes, so you cut out your set, the vanishing of the zeros of this polynomials, and the spectrum of A is the complement. So spectrum of AS is the complement to the set of zeros of SIs. Meaning that you consider prime ideals, yes, so irreducible varieties, and there is some subtle moment, they should be not contained entirely in SIs. So they could have the points on these components, but these varieties, these irreducible varieties that correspond to prime ideals, they should be just outside of sets Si, and you keep on the back. And so this is spectrum, so that if you want to check this decomposition, notice that also you can think of converse map. So if P, so if pi is inside spectrum, you can consider P as. So this is extension of ideal. This pi is I have a formula. So you are writing down I of pi. So you are in as, and then I of pi is not ideal anymore. So you generate the ideal by multiplying of the elements of the ring. Still it is additive, but you have to be able to multiply by any element in the ring. So you should have denominators to allow all possible denominators. And this, so if you map like this, so this map is non-trivial ideal. Trivial. So meaning it's not the whole ring. If pi, intersection of pi and the S is empty. And under this condition, this is bijective operations. Yeah? So if you have the ideal with this condition, you can construct the ideal in spectrum of AS, and vice versa, given ideal of spectrum of AS, you take the inverse, it is prime and has this kind of properties. So if you have the property that if you decompose P1 in N1, etc., P, K, and K, yeah? So you can, and you want to calculate the multiplicity of P1, you can consider multiplicative set equal to A without P1, which is multiplicative set. Because if you have two elements which are not in prime ideal by the property of prime ideal, their product is again not in this prime ideal. So this complement form the multiplicative set. And if you use the previous observation, so if you localize by S, so you consider I of I times AS. Yeah, so this means that if you take J and localize it, yeah, so notice that all PIs are maximal in our ring. Yeah, so that means this will be AS. So since it is not, if you take S and intersect it with Pj, so this is a complement to P1. Yeah, so if it is empty, yeah, so that is condition that this map is non-trivial. This implies that Pj is inside P1, but this is not possible since j is not equal to 1 and Pj is maximal. So not possible. So since Pj is maximal. So this, and if you have an element in Pj which is inside S, after passing localization it becomes invertible, so that you have a unit in your ring, in your ideal, and this implies that this ideal is the whole ring. So when you apply this localization procedure to the product, then you keep only this P1 and 1 times AS. Yeah? So, or formally this is I of P1, but we can, since we work in the setting that we have non-zero divisors, so just in our ring we do not have zero divisors, then you just, this I is just on 2. Yeah? So you have this property, and this tells you that in order to check these conditions, yes, so you have to take your Dedekind ring, you have to localize this expression, and you will have that your ideal will become a power of your maximal ideal. But note that in Dedekind ring, local ring, so P1 is just, so P1 is generated by one element, which is called uniformizer, and called uniformizer, and this reduces, this equality reduces to that I, if you take, so let me now skip the notation for I, so I times AS is just P1 in some power. Yes, so that yes, that is yes, what actually you have to check. So this is just reduces to divisibility by the power of fixed L. So maybe it is good point to make a break, and after the break we shall pass to the theory of ramification. So now I want to speak about ramification theory, and for this I should explain briefly some geometric situation that is underlined, just illustrating the picture. Yeah, so ramification. Yeah, so suppose more generally you have F is a map of algebraic varieties. So just of course for those who do not know, so you can skip them, but I mean this is some kind of important illustration that really important for understanding what is going on. So if you have two algebraic varieties, yes, so affine, for example, affine algebraic varieties, you have the set of so affine varieties are just those what are defined by system of equations in affine space, and you just obtain them as taking polynomials modular the ideal that is generated by the system of equations. And so the regular functions on them is just so the well-defined object. So if you have regular functions, then if you have function downstairs on y, so you can consider the pullback of this function. So given phi inside k of y, you can define the pullback of this function, that is function on x. So simply actually by composing, so phi, if phi is a function, it can be viewed as a map to a affine line. So it is just the value, and the value is just the coordinate of At each point of y, phi has the value, and the values can be thought of a point on coordinate line. So you can, so given phi, you can consider a new function on x via composition of these two maps. So by definition, calculation of phi star of phi on x is just composing f and phi. Yeah, so I'm writing down f of x. I get a function on y, and then I can take f, and I get a value of this function. And so the map is a regular map of affine varieties if this pullback, and actually this is if and only if this pullback maps the regular function on y to regular function on x. Yeah, so that we have f star that maps k of y into k of x. So more general, so here you have we will have the property in our case that actually k of y is you have inclusion. So if this map is dominant, so meaning the closure of the image is equal to y. So if the closure of the image is equal to y, then f star is inclusion. So and this is if only inclusion. So this yeah. So then you can ask what happens with subvarieties. How we can define it. So subvarieties in X are defined via ideal in X, yeah, in K of X, so Z. And you can think of W, which inside Y, defined by the W, IW, the ideal of functions vanishing on W. And then you can ask about the following properties. So you can take W and take its pre-image, for example. Then, of course, this is a subset of y, x, and if the map is continuous, then pre-image of closed subset is closed. So this is closed subvariety and should be defined by some ideal. So it's closed subvariety, affine subvariety. And defined by ideal, and let us see how we can define this ideal. Yeah? So in order to check that, so we have to take functions phi, well, psi, for example. So we have to take functions psi, and we have to take, so check that psi of z is equal to 0 for, yes, so psi of x is equal to 0 for all x inside f inverse of w. How we can, so we have to understand what condition on the function we have to supply in order to understand that the function should be inside W. But notice that the x is inside the f inverse of W if f of x is inside W. And you are checking this condition by taking all elements in the ideal of W and checking that if they vanish on f of x. So if and only if just phi of f of x is equal to 0 for any phi inside the ideal I of W. And this implies that this condition can be rewritten as via pullback. So this means that f of phi, f star of phi applied to x is equal to 0 for any phi inside wi. So what we have obtained, so in order to check that x is in the preimage, it is sufficient to check that f star of x or f star of phi is vanishing on your given point. So this means that ideal of preimage. So these questions, of course, do not form the ideal. So, for example, you may think of that you are taking generators for W, and you obtain the finite number of equations, and by taking pullback, you obtain a new system of equations that you use, and then you just generate ideal by this system. So ideal F inverse of W is generated by phi star of phi, where for any phi in W, I so it is just generated by phi star of I. So notice it is not the ideal, so you obtain extension. Yes, so this is operation is called extension, so you have to take f star of I and generate the ideal that can be written as you need to multiply by all elements from Kfx. Okay, so this will be ideal. Now this is ideal of Kfx. And vice versa, you can think of image. Yeah. So, but the problem that image, so we can take Z and try to take its image, and then we want to obtain ideal generated by the image. Yeah? So, that ideal functions from vanishing on the image. But in general, so that there is a slight problem that. Yeah, so let me explain how we're doing it. So just ideal of the closure of the. So the problem is that that f of z is not closed. Yeah, so if you consider very easy algebraic map, so for example, you can take hyperbola on a fine plane and just project it. If you project it, you will get everything without zero. Yeah, so that if you take x, y equal to 1, yeah, so then after projection you will get all affine line without zero. And this is not closed, Zariski closed set. It is not defined in A1 by the system of equations. So you have to take the closure. So you have to take the functions. So this psi inside k of y, such that phi vanish identically on the image. So you take the image, and this, so the such function vanish. Yeah? So let us. So that means this is called closure, and we shall check how to do it. Yeah. So you have to do the following. So you have, suppose you take a point inside Z. Yeah? So you have to take f of Z, and you take the function psi that should vanish on the image. Yeah? But notice that if you apply phi in this way, so we search now for psi that vanish for any point of z inside z. But this can be, if you write down psi of phi of the z, this is just f star of psi, yeah, applied to Z. Yeah, so meaning that, so let me draw this picture that you have Z here, yeah? So you have a point. So you map it somewhere to f of z, and you have to check that this is the image. You are checking that actually pre-image of f of z contains z. I mean, if you want to take this w, yeah, so you instead of checking that z maps to w, to check upstairs. So let me write down that f of z sits in w. It is equivalent to check that z sits in the preimage of w. But checking about this preimage is just checking that. If you think of w that is generated, so we take here w, the variety corresponding to vanishing of the function psi. Yeah, so we have to check that the w that corresponds to the vanishing of function, it contains the image. So this means that you have to check this property, and for one function, yeah, so we noticed that this is the equation that describes preimage. It is just f star of phi equal to 0. Yeah? So we have to check that this is equal to 0 for any z. So, and this implies that this function f star of phi belongs to ideal I of z. So this should vanish for all points of z. And this implies for the function phi, this means that phi belongs to preimage of I of z and the inverse of the pullback. So this means that you have homomorphism and you just take, ideal defining f inverse of z is just pre-image of the ideal defined by.
So how would take f minus 1 of z?
Ну, в смысле, это не обратный
Не, вот
гомоморфизм.
здесь я понимаю, они же. Идеал f от минус 1 от z.
В смысле, замыкание. Ой, F, извините. Опечатался и не заметил. Хорошо, спасибо, что следите. So, so this explains that we have two natural operations, yeah? So that corresponds to the image of the varieties and preimage. So in our situation, of the Rilke's extensions, we have the following. So we have two fields, actually. And here you have subring A, for which fraction field of A is equal to K. Yeah? And we also have B here. So such that B is integer closure. So B is integral closure of A in L. And morally, this is this thing what we consider from geometric point of view, it is finite surjective morphism. So this is this is spectrum of A. I mean, meaning that if you have inclusion of rings, you have opposite map of prime ideals. So we are taking so if it is I, you can map the set of prime ideals. Yeah, we are taking. So if you take P to be prime ideal in B, so beta, so this is prime ideal. Notice that preimage of prime ideal is also prime ideal. So this implies that beta intersection of A, which is just I inverse of beta, so this is also prime ideal. So this gives you the map of spectrums. Spectrum of B maps to the spectrum of A. And this will be finite map, meaning that, so first of all, on spectrums you will have, so this thing will have the following geometric properties that we will discuss. So geometric properties. So this map of spectrums is surjective. Yeah, so this can be viewed as a star. Не, ну как-то тут звездочка, ну, хоть I inverse, да? So geometric properties. First, the map of spectrums is surjective. This is a surjective map. Second, it has finite fibers. So the so meaning that now we have to explain what it is, but let me now we shall start understanding it, what I mean by that. So finite fibers. So meaning that if it was of course this thing can be done in purely geometric situation. For example, you can take a fine curve. Curve means that this so you have a fine variety, so meaning it is just defined by the system of equations, and its ring is one-dimensional, has crude dimension 1, meaning that you will, as closed varieties, you have only a point on the curve itself. So, collections of points, finite collections of points on the curve and the curve itself. So this also this we can assume that the ring is Dedekind, but this is not important here at this moment. So you can take a point and take its preimage. So formula. So you have So you can have a curve, and you can take the fraction field. So this regular ring of functions on the curve. You can take finite field extension. So meaning that finite extension. So we have. So we'll start it. And then you take algebraic closure. So then you will have the ring, and you will have inclusion of the rings that allows you to say that upstairs is some algebraic separate, and there is a morphism between them. So you can observe that if you have this kind in general settings, that if you have this finite morphism, then the dimension is the same. So the dimension of x is equal to dimension of y, if you have the property about integrality of extensions. So if B is finitely generated module, then so just So suppose we just then dimension preserves. So let me say it as a remark. So if you have inclusion of kfy inside x, and just kfx is a finitely generated module over kfy, this implies that this implies that the dimension of x is equal to dimension of y. We shall see this explicitly in our case, but this is a general setting. So I mean, you do not have to assume that A is determinant here. Yeah. So and for subjectivity, you also I mean, this is enough for subjectivity. So having conclusion. Yeah. So sometimes one do not say, I mean, if one speak about finite maps, it is convenient not to assume inclusion, but assume that there is homomorphism of the pullback map. Yeah, so that this maps to kfx, and this is kfx is a finitely generated module. So this really gives you that. For example, it can happen that you have just kfy maps surjectively to kfx, and this is corresponds to closed embedding of one variety into the other. Just with defined by the ideal that is the kernel of this homomorphism. And so that's why I'm speaking about conclusion. Yes, so to to say that the dimensions are equal. Yes, so otherwise we have only inequality between the regions. So this and finite fibers means, of course, you take prime ideal and take preimage. Yeah, so so here you of course can think of all prime ideals all prime ideals that under operation I maps to pi. Yeah, so we can form the for pi we can consider beta lying in the preimage meaning that, and this our condition will be like this. I mean, from the this condition is just a beta intersection with E lives in pi. Yes, so preimage, so ideal, so variety lives in that. So this is precisely what we did. So Z lies in the preimage of W if and only so if phi of Z lives inside W, yeah, and this is precisely the ideal that defines preimage is obtained by the intersection. So condition is that this is equal. So actually, so this should contain pi, but pi is I mean, so between ideals, this should be opposite inclusion. Yeah, so the ideal. So this is ideal defining f of z. So you should have it contains pi. But and when the ring is dedekind, it is pi is maximal, so that you have equality. Yeah? So when A is dedekind, A is dedekind, so we have a condition so P is maximum. So beta intersection of A is just P. Yes, so you have do not have one other option. So we say that the beta is lying over P in this case. So this is some kind of, so we say that beta is lying over so this, of course, yes, so this is standard language in the literature. Of course, people really meant this kind of thing when they were discussing this condition. So also you can. So this is saying what the ideal in is inside the preimage, but we may think of the following. So we can take the ideal that defines preimage itself. So we can start with P, and then P inside A, and we can form. So P is if you put P inside B, it won't be an ideal anymore, but you generate the ideal, and P beta is ideal corresponding to preimage. Preimage of the point. So geometrically on our picture, we have so you have P here, and you have preimage that corresponds to ideal P times beta, and you have somewhere, if you have a finite map, so you, I mean, if this is a point, over P there should be also varieties of dimension 1, so they should be just maximal ideal B1, B2, etc., Bk.
Dimension 0.
Of dimension 0, yeah.
Mm-hmm.
So, but of course, it may happen that when you consider, so let me draw the simple example. So, note that if you take parabola,
yeah, and ideal PB is like we multiply on the element of B, yeah?
I mean, all the linear combinations.
Mm-hmm.
Yeah, so this is, I mean, always when, I mean, you just can say that you take P and just multiply, I mean, this is not, of course, the set of pairs, the element from P and the element from P, but so naturally when you're speaking about as a answer, so you take all linear combinations.
Mm-hmm.
And also notice, I mean, so here we came to the point when, so it is natural to ask the question, for example, do you know what is generalization of notion of prime ideal for non-commutative rings? I mean, for commutative rings, it is just the question, I mean. No, actually not completely in different direction, but because to non-commutative setting, and this most of the things that I'm talking today are really just can be generalized also in non-commutative setting. So that's why I'm saying this. So if you have pi, yes, so the pi was prime is if either a modulo pi is domain, yeah. So or you have the property that if you have a about what is the right notion of primeness in non-commutative setting. Yeah, so notice why it is a little bit complicated question. I mean, from because if you take matrix ring, so you may think of classification of I mean the best theory you obtain is when you go to non-commutative world is the following. You take the ring module, its radical, and you obtain the semi-simple ring if it is Artinian, if A itself, the ring you have taken is Artinian, then it is a sum of the semi-simple ring is a sum of matrix rings over the bodies. Yeah? But if so that means that matrix ring is example of a good. This definition is stupid from the viewpoint of matrix ring. If you assume that A mod P has no zero divisors, it is completely useless because you do not have matrix rings. Yeah? So in matrix rings you have many zero divisors. So that means that if you want to have some definition, so at least this is bad. So what is good? So surprisingly, you may, I mean, you can write down explicitly the definition, but it is a little property that we have derived out of this principal theorem on arithmetics that says that if P contains I and J, yeah, then P contains I or P contains J. And if you put to be two-sided ideals, yeah, so I mean, so the question is where you want to generalize the property of being prime. And this should be generalized in two-sided ideal setting. Because, I mean, if you want to multiply them, yeah, so just you lose some information about the other ideal if you multiply. So at least this should be about two-sided ideals. So these are two-sided, and P also is two-sided. So if you have this property, then P is prime. And this means that out of this, you do not have, but if you think what are two-sided ideals from the viewpoint element-wise, if the ideal is principal, then you take an element and multiply it by the two sides. So this property, this means that this property should be stronger. So I mean you should put C inside the A and B. And if this holds, then this is prime. So that is the right notion in non-commutative. And if you are thinking about the multiplicity, yeah, so that also you are thinking about this ideal. Yeah, so the example can be thought as follows. So you have, you can think a map about the map of a fine line into itself, and coordinate-wise, you can map a coordinate to z squared. This means, what does it mean from the viewpoint of the pullback? Yeah? So this means that here you have also a coordinate t. Yeah? So meaning that taking coordinate z squared is, so if I denote this map by pi, so this pi and this is pi star, yeah? This means that taking this square is evaluating. So the square is not just a function, it is a value of the coordinate. So it is taking t on this square. Yeah? On the point corresponds to the square. So this means that it is taking t of pi of z. Yeah? I mean by definition. And this is a pullback. So pi star of z. So z is now a function, so it is coordinate on A1. So this quality
Shouldn't be
pi of t calculated in z.
shouldn't be pi star in other direction. Like if it's
Да, да.
Ага.
Нет, просто это не
Не
p квадрат, а это поточное. В смысле, это p.
Ну да.
No, p. Yeah, so this means that calculating of this square is just taking pi star of t and taking calculating on z. So from the viewpoint of the coordinate functions, pi star maps t, so it is a map of the ring k of t to k of z, yeah? And it maps t to z square. So if you take, I just wanted to speak about the motivating simple example. So if you take a point here, yeah, so you can do the following. So you can consider pre-image of this point. Yeah? And also, so clearly there is zero, yeah? And the pre-image of zero is just zero, but geometrically, if you put the graph of the map on the projection, it will look like writing parabola and taking the corresponding projection. So this really tells you that this kind of thing. So you can. So let us calculate this thing explicitly. Yeah? So this means that you have to take. So for example, over z and over a. Yeah. So if you take it over z, so that means that you have ideal. So case first case. So t is equal to 0. So you are looking at the point t is equal to 0. Ideal t. You take pi star of ideal t, and it becomes z squared. Yeah? Z square time, it is notice that pi star of k of t. Yeah? So pi star of ideal generated by t. Yeah, it is what? It is just z square times k of z square. Yeah? So if you take, so ideal generated by t is k of t. K of t times t. So let me put it that it was pi star of t times k of t. And you see that here, you see that this is not ideal from the viewpoint of the ring. So here you have to generate ideal by z. So this will form, it will look like z square k of z. You have to add more elements.
What? So
Ну как, это же z квадрат, его нельзя на, это полином от z квадрата, но вы можете брать z квадрат и умножить на полином от z. Поэтому тут нужно, ну я просто это хотел проиллюстрировать на очень простом примере, где понятно, что, ну как бы, чтобы вообще подробно разобрать, что происходит, ну как бы, что этот вопрос нет. So now t is equal to a, and again there is a question what is a. So A can be, it can happen that you can extract square root of A or cannot extract. If if you write down P star of T minus A, it will look like, so now I skip this step of generating ideal. So P star of T of A times K of Z, let me write it from the beginning. It is Z square minus A K of Z. So this here you have two options. So if you can extract square root, so you have square root exists. So you can write this down as Z plus square root of A times Z minus square root of A times K of Z, and this is not simple ideal. It is decomposed into two products. Or just square root does not exist. So this is ideal precisely as Z square minus A. And notice that you can consider quotient by this ideal. Yeah? So if you consider quotient by this ideal, it will be a field K. Yeah? But if you take quotient of this ideal, so K of Z modular K of Z modular Z square minus A, this is quadratic extension of K. Yeah? So you have the following options from these three moments. So you have the option where you have, and notice, where over initial field you have, I mean, if you take a point and square root does not exist, does not lie in the field, in K. Yeah, so then you cannot distinguish between these points, and then they think you may think like a thick point, because when you extend the field, then these points become two different points. So this is maximal ideal, but geometrically, if you allow to think of this like you are sitting in R, you have the thing that corresponds to the preimage, but you do not see it as the coordinate point, and you will see it as the two different points when you extend the field to C. Yeah?
Yeah, so if we don't extend
The field, yeah.
this
this is
point,
just so this is one thick point.
As if t equals 0, it's also one thick point.
It is not thick point. It is point with multiplicity. Yeah. So this is so here it is a point with multiplicity. Нет, то есть это вот как бы это свой вот тут есть два типа точек. So we have two types of points. So here there are coordinates. So here we have types of points and types of preimages. So this property of being thick or not thick, it is a type of points on a fine line itself. Because you have different type of maximal ideals. Because modular this maximal ideals, you obtain different fields.
Yeah.
And one is quadratic extension of the other, and we see that it is thick in the sense that it is a union of points. Yeah?
Yeah.
And here the thing is that it is not thick as a point. The preimage, so this means that preimage has some thickness. So it is a property of preimage. So the tangency, yeah. So that we call multiplicity.
Yeah.
And as a point on a fine line, it is a coordinate point already. Coordinate point. So this Yeah, so this motivates us to do the following, and I just yes, I emphasize that this is more or less general example, so to think of, and just I mean to imagine something about that. So now let us pass to general theory. So general keys. Yeah, so you do the following. So you start with pi, and you consider pi b. Then we can think about, we can start writing down the composition. B1, BK, EK. So notice that automatically this BK, so BI, of course it contains the products. Yeah? So this is the composition. So sorry, I should say something about it. So the composition. Yeah, so we have to notice that. So sorry, let me erase it because just. Not because it is not true, but because we have to explain something. So just proposition. So suppose we're in the following case. So suppose A is integrally closed. In K, crude dimension of A is 1. So it is the Dedekind ring is Dedekind. So L is inside K is finite extension. And B is algebraic closure. B is algebraic closure. Integer closure. So integer. Of A in L. Then I claim that B is also Dedekind. Yeah, so the thing is that you have to prove here only a statement about this. We have to prove. The statement about dimension. And what we have to establish that if you have the sequence of ideals in B, so beta 1, beta 2, etc., beta k, so sequence of prime ideals. it will, the dimension is the maximal sequence of prime ideals. So we have to prove, so at least we have to prove the following, so that we have to prove that in B you start, so B is without zero divisors, yeah? So you cannot have the sequence of this form, yeah? So sequence of prime ideals where where you have strict inclusions does not exist in B. Yeah? Does not exist. But here you have a rather simple situation. So notice that you have to do the following. So you have to intersect. So I claim that we can intersect it with A and obtain the sequence of ideals in A. So what you have to notice is the following. So first, for non-trivial, so that if you have sequence here, you will have non-trivial sequence in A. Yeah? So first you have to notice that so here is strict.
Why strict?
Yeah, so we have to notice. I mean, so first of all, just consider the intersection of beta 2 with A, so this is not equal to 0. Yeah? Why? Just this is very easy. So you have to take all elements of B are integer over A. So given B, we shall precisely construct the element which is non-trivial. So now let us do it. So it is a root of, so let me put just B here without index. Yeah, so root of equation, of integer equation. So this is just b to the power n plus a n minus 1, b to the power n minus 1, etc. plus a0. Yeah, so notice that, yeah, so your equation, since we do not have zero divisors here, so we start with a0, which is a non-zero element. And notice that the element a0 itself, it is just minus element of b times the polynomial. Yeah, so just and this is an element of beta. Yeah. But this is smallest coefficient, it is an element of A. So we get non-zero element of beta intersection with E. So at least we know that this is not zero. Yeah? So then we see that this beta i's are since A is dedicant, so this chain is you have only one maximal ideal, one prime ideal. So this means that since beta I intersection with A are prime, so you have the property that beta I intersection with A is equal to some prime P. And this implies that B modulo beta I is finitely, so is integer. So B is integer over A, all elements is integer over A. So we can consider the map, the natural map from beta to B modulo beta. And if you look at the restriction of this map to A, so this means that it is A modulo the kernel of pi, restriction to A, so which is just A kernel of pi is beta. Yeah? So this is A modulo intersection of A with beta. Yeah? So which is denoted as A modulo P. So since beta is integer over A, this implies that beta modulo base I is integer over A modulo B. Yeah, just by using the same integer polynomials. Yeah, so by using the same integer polynomials. You just can reduce it modulo P, and since highest coefficient is 1, yes, so they're still integer. And this implies, but if you have integer extensions, if one is a field, then the other is a field. So if you have B and the extension of A and the B, so let me recall them that if B is integer over A, yeah, so that A is a field if and only if B is a field. Yeah, so B has no zero derivatives. So this means that P was maximal. So since A was Dedekind, yeah, so here, since A is Dedekind, so that means that P is maximal. A mod P is a field. So this implies that B mod beta is a field. So this means that beta is maximal. So beta I is maximal in B, but you have beta 1 is inclusion in beta 2, so this means that beta 1 is equal to beta 2. So this chain is, consists of one ideal, so this means that the dimension of beta is equal to 1. So more or less, we didn't use anything from the Dekindness. So that
Integrality.
yeah, so we used on the integrality, but we proved if we are thinking about integrality, that means that over irreducible variety there exists only you do not have you do not have the picture that you have. If you do not assume the Dekindness, you can do it via localization, and that will your property will say the following. So that if you have an integral map, so integral extension, you do not have the property that you have a variety and subvariety that maps into the same variety downstairs.
Mm-hmm.
So out of this you actually prove that if you have finite map, then under the finite map the dimension preserves.
Mm-hmm.
So so that means that if you consider so the chain, so that it is if you have strict inclusions, then downstairs it is also strict.
Mm-hmm.
So then, yeah, so here, so we are finishing it by this observation, and then next time we shall apply this observation that you can take our ideal now p beta, so as I started saying, so you can take p beta, and now you can decompose it. As, so since beta is Dedekind, so now you can decompose it into the product of some beta key. And then we shall discuss what are these guys, which are called multiplicities, and so just all things related.
Это индекс.
Индекс ветвления.
Да, это индекс ветвления, да, будет?
Да.
Ага.
Ладно, спасибо.
Спасибо. Кстати, надо спросить.